Thank you very much to the organizers for inviting me. Of course, it would be nicer if I could be in Buenos Aires, but that's life. So what I'm going to talk is based on some papers with Renato Fontes, Domingos Marchetti, Tom Mountford, and Daniel Ungaretti. And at the end, I will touch a bit on some uh, ongoing work with Marcelo Hilário, Daniel Ungaretti, and Daniel Valezin. So we start by our old contact process. For some reason, this doesn't want to. Our old contact process, which is not as old as me, but it's almost 50 years old. So introduced by Harry. So it's a Markov process on the 0-1 configurations on the vertices of a connected locally finite graph. So with the interpretation of 1, meaning that the site is in fact, the vertex is in fact at time t, and 0 that is healthy. And in fact, the individual transmits the infection with a given rate, which is the parameter of the model, to each of its healthy neighbors, and heals with rate 1. So the interest of this process is that it presents a dynamical phase transition. That means if you have a lambda, there is a critical value which is bigger than 0 and finite in a quite general situation, that if lambda is less than this value, then the infection always dies out starting from any finite set. So this upper index here, upper thing here means the initial configuration. And if lambda is larger, then there is a positive probability that the infection persists. Okay, so this process is, we can think of it as a percolation model, as the percolation structure which is behind this process, which is just, you think of a space-time graph. On each edge, you think of independent Poisson processes with rate lambda in each of the directions. And you think of crosses which represent in this case, independent Poisson process with rate 1. And you think simply of constructing a path, the path, which means that the path can move from one vertex to another only when there is an arrow through the arrows, and cannot cross any of these crosses. So they are cuts. So it's a percolation thing. It's oriented in time and not in space. So, well, this kind of thing has been used also for the more general, for the representation of quantum Ising model, but then it's not oriented in time. So thinking this way, and as a percolation model, you may naturally replace your point processes by more general process. So this is the same picture as before, just made a different picture for us to call attention that now we have different process. So the point process NX and NXY, the cures and the transmissions are now, in principle, you can think of any quite general point process, but the construction is exactly the same. And you are into the first question that you might ask, if you have percolation or if you have survival. So that's exactly the same thing as before, but same construction, but now your processes are not Poisson anymore. So you do not have anymore the Markov property, of course. You may lose other nice properties. For instance, the FKG property might be lost depending on your distributions. And but you have some things that you might do with some conditions on your point process. And the one that I'm going to focus now is I'm going to think of your graph being the ZD, the square lattice in any dimension. And I will keep the transmissions as Poisson, though this can be more general. But the cures will be a renewal process. So I will take at each X, you have an independent renewal process. All of them will have the same interarrival distribution mu. So the NX, I'm writing RX just to point out that this is a renewal process, just to think, but it's the same as before. And of course, we assume this measure to be non-degenerator, otherwise there is nothing funny at all. So the point is that now if we have at a given time t, what's going to come will depend on the age of my process. That means the time since the last renewal. You have not anymore the independence property that gives you the Markov property. So, but the questions all make sense. And the first question that we got interested in this was, for which measures mu can we guarantee that whatever is lambda, you do have survival? That means the lambda critical that we had before, which was a number, now is it depends, of course, on our measure mu. We want to ask when is it equal to 0? That was the first question that came to us, and because our motivation to get into this, in fact, came from, we were looking at long-range, one-dimensional percolation process models, and started asking ourselves if by adding a small nearest neighbor in the transversal direction, we would have percolation for a certain class. So it came to this question. Naturally, this was easier in some sense. Okay, so since in the case I'm looking at that the transmissions are Poisson, you of course have a monotonist in lambda. So asking this is the same to ask that if we start with a single infected individual, then the infection will remain forever with positive probability, no matter how small is lambda. That's the first question that I want to say something. And of course, since now you need good control on the renewals, because, well, it's not always the same. So it's clear that in some cases you might use the you need to use some strong theorems which are known under some conditions and regularity conditions, like Ericsson. There are these other two more recent papers by Xi and Caravena-Doni, very recent, completing the solution of the strong renewal. But well, because here usually you have a lot of regularity in your measure. With less regularity, you can do something that is enough to answer the questions we have in mind. And the main ingredient for that is to have some lower bound on the tail of the residuals. That means a lower bound on the probability of having a gap, a big gap, empty space without any cure marks, because you are interested in showing that it survives. So this kind of estimate that you want to get to use, and this can be proven under more relaxed conditions than the usual domain of attraction of stable distributions. So, but that was our first goal, and a first theorem in this direction some time ago already is that if your tail is heavy, then with some regularity that I don't want to spend much time now, you do have a positive answer. It is, of course, in any dimension, because once it survives in one dimension, it survives. In fact, to show this is enough to have just Z plus as your space. And this is kind of quite clear that, well, if you have gaps not too far from each other, then you can just tunnel your infection and construct an infinite infection path. So it's kind of quite clear that from the previous estimate, which I said on the residuals, on the gaps, then you should have this one. But of course, this is not a full answer to the issue, because for the contact process on big graphs, you might have that the infection remains forever, but it goes somewhere and doesn't return to where you started infinitely often. No? That means what is called the weak survival. So it's natural to ask a little bit more on this. And this more complete answer to this kind of question has been done in this more recent result, which is still not published, but it's a preprint. I mean, under the same conditions, you do have a complete convergence theorem in any dimension. That means if I take any lambda and I start with an initial configuration, of course, not empty, because otherwise there's nothing. But anyway, initial configuration, then I will have convergence like in the contact process with a mixture of the empty configuration and the full configuration. So in the contact process, you have here a non-trivial measure. Here, this non-trivial measure is trivial in the other direction. It's 1. This is weak convergence. So it means that if I look a finite box, then I will have everyone infected in this box with large probability. I mean, give condition on survival. So I have a mixture of these two measures. So one important thing for this, and what comes from that's the main ingredient, is to say that condition on survival, and if your time is very large, in a region which is not so large, I mean, grows much less than the time, this like logarithmic, you have someone in this region which will be infected during all this time. So this guy will propagate the virus or something like that. That's the ingredient for proving this. And proving of this, of course, involves the analysis of the renewal. Okay, I didn't make very precise the conditions which we use, but what you should think is that they include, of course, those which are in the domain of attraction of a stable with alpha less than in 0, 1, less than 1. But they are more general in the sense that they allow your tail, the tail of your thing, to oscillate between one alpha and another alpha prime and so on. So it can get more flexibility here. But this is a basic example to keep in mind, okay? So when we are in this case, one can say more. And let me recall two results. One which was proven by Renato Fontes, Pablo Gomes, and Remy Sanchis, which is the following. In this case, but here they use the regularity. Even if you have a finite graph, you might have percolation. There is a interesting phase transition in the number of vertices. So your graph is anything finite and connected. And there is a phase transition in the cardinality of the vertex set. So for a vertex set larger than something, that depends on alpha, you do have survival no matter for all lambdas. And if it's less than that, you don't have survival for all lambdas. I mean, you don't have survival. I mean, fix any lambda that you fix, you have this. So it's a more precise result. I'm not so sure that they truly need this restriction, or if they use that because they rely on the stronger renewals theorem, which for alpha less than a half, it requires some further conditions, as in Caravena and Done. So I'm not so sure because I don't know too much in detail this. This is one thing that you can do. Another thing, and that's what we did, is to investigate the convergence, that the result which you mentioned about the convergence a little bit more. And this is by saying something more about your your process when you condition on survival. And this is basically saying, I state the theorem here because I think that I am already moving too slowly, which is the following. I mean, so since these tails are very, very heavy and you have these big gaps, um, depending on alpha, and as I already said, you do have someone providing this virus for a long time. So at least if alpha is really small, that means that it's really heavy. Then given that you survive, and if you know the age, that means the age at the vertex you are looking at, that means you know the time since the last renewal, then if you do expect to have people infected it from somewhere. So it's basically the probability that you have a one is that there has been you have 2D neighbors, there is a lambda. So this is just that as if you take 2D exponentials of rate lambda during this time, one of them will ring one of these clocks. So you do have that. When alpha is bigger than 1/2, you need to replace this 2D by something else, like 2D minus K, where depending on where is alpha. But this is already more specific. I don't want to enter now. Okay, this you can say something very strong, very precise in this case, but here we did use this regular variation issue. Okay, now you may look at the question from the other side. Okay, I have some sufficient conditions for lambda to be 0. Now, since it's too ambitious to determine exactly when it is, so let us look from the other side. When can we say that that lambda critical is positive? There is a trivial thing, at least in this case of Poisson, that if you have a finite second moment, then it is positive. This is very simple because you just think that the lifetime is integral. The time between two, I mean, if I have a look at any time and I think of the interval, the maximum interval without cures that contains this point. This will be integral because the interarrival has second moment. So thinking of that, it's clear that you can make a comparison with a branching process and get to this. So, but this has a huge gap now because here is 2 and we want to get to 1, of course. So we need to improve that. And well, in order to improve that, there are some possibilities. One that I mentioned here because I think it's useful that it could be explored is if you assume that your interarrival distribution has a density which has a decreasing failure rate, then you can construct your renewal process as an increasing function of a Poisson point process on the plane. And so due to the fact that this is an increasing function, you get FKG property for your process in the sense that increasing events will be associated in this usual way. We have positive, the probability of an intersection is bigger or equal than the product of the probabilities. Here increasing means increasing in the errors and decreasing in the cure marks. That means events that involve a positive information about having path, like having a path from here to there and so on. This is the meaning of increase. So this is interesting because it might be explored in order to give further information of the process. Now, FKG property is something kind of useful. Using this, in one dimension, we could prove some time ago already that if you have a moment of order bigger than 1, then you do have a positive lambda critical. Using this hypothesis, I think it's okay because it's some nice thing that can be explored further to say more. The main problem here is that we have this restriction to one dimension because we did use path crossing to connect, to construct a path out of other paths. Like you have some control on the horizontal, on the space crossing, and so on, and you do use them, concatenating them to get a vertical path, and then by using the usual square root trick, you get an estimate from the probability of making vertical crosses. That's what you need. So it's a little bit, it's bad in this direction. So, but that's one. I mean, I mentioned this one here mostly because I think using attractiveness, using this thing, one might be able to say something more about the process. I mean, we are just giving a few basic answers. No? So important improvement in that is that's the best result we have so far about having positive lambda critical is this one, which is still in the preprint that I mentioned. So if you have something a little bit more than integrability of your measure, and so, and this is not just a little bit more, but it's specific, it's the best we can get with our proof, with our method, but of course it shouldn't be the best, you know. So we consider the measure mu, which satisfies this integrability condition, with some theta here that there is a lower bound that depends on the dimension. So, and in this case, we can prove that lambda critical is positive. I will give a little bit of say a few things about the proof if I am able to reach there. I see that I go a little bit too slow, but anyway, that's so. Of course, it remains the main question is if one can manage to push this down up to integrability. That's, I think it's a hard question, I guess, but we were not able so far to know if lambda critical positive, if and only if finite first moment, or if at least if finite first moment implies lambda critical positive. We do have examples which are in the domain of attraction of stable one, and lambda critical is 0, but they have infinite average. Okay, so that's the thing. So touching a little bit this more recent work, ongoing work that I mentioned with Marcelo, Hilario, Ungaretti, and Valezin, we took back the situation of a dynamic environment, more or less in the same spirit as Marcelo spoke today. So we think of a dynamic environment in the edges, and based on this environment, you have a contact process. So this model was studied before by Hemenick, and there is also this more recent paper by Linker and Hemenick. So which is the environment for them? The environment is the dynamic bond percolation on ZD. The parameter of the percolation is P, and there is a rate or a speed V. That means the edges, they open with a rate V times P, and they close with a rate V times 1 minus P. So the Bernoulli product Bernoulli measure is invariant, of course, here. So it's just the well-known dynamic percolation moving with this speed. On this process, so the environment, the edges are opening and closing as time goes by. You consider the classical contact process with rate lambda and 1, the usual contact process. The only thing is that only the open edges can contribute to transmit the infection. So people get on quarantena for some time, then they go back without masks and so on. That's the way it goes. So the results, Linker and Hemenick, they proved several results which worked for a wide class of graphs. of graphs. One exception was what happens as v tends to 0. As v tends to 0. No? So let us call lambda critical. In this case, let's call it lambda 0. That's the critical value in this situation. While you have your v or your p fixed, the lambda, the infimum of the lambda, such that you do have a positive probability of survival. So of course here it is monotone in lambda too. So to answer, to generalize what they did in one dimension to higher dimension, we proved exactly that. If P is less than P critical, as V tends to 0, the lambda critical goes to infinity. Somehow. This is, they had proven this in one dimension, where of course here is 1. So we extend to higher dimensions, and well, with a different argument here, say if P is bigger than PC, then this stays bounded. And well, there are some conjectures where it should be the limit as V goes to 0, should probably be the lambda critical in the infinite cluster of P. So this is the scenario. That is something that they already knew, is that there is some value of P such that below you have this region where lambda is infinite. But we don't know P1, of course, we know it's less or equal than PC, but we don't know a better estimate than what they have done. So I think I have 3 minutes, no? So let me just say a few things about the scheme of the proof. So now I want to prove that there is no percolation if lambda is small. So you want to find cubes. So the first, the concrete estimate that comes from the renewals is that, well, if you have something which is integrable, then you have an upper bound for the probability to be without cubes. And this depends on the function you put here. So if the measure is integrable, you can always find an f, but your estimate might be very bad if f grows very slowly. So you do have that, and then you want, based on that, to apply some kind of renormalization methods to estimate the crossing probabilities. Now you have boxes that you need to find suitable scales and want to control the probability to find a path. So for this box, you have many estimates that you have to do, 4 estimates that you have to do. In fact, 2, temporal and space. But, sorry, I always have this trouble with the mouse. No, that's usual with old people. So you want to find estimate for the temporal crossing, or also for the space crossing. For some reason, something here disappeared. Because this was before. So you want to find this and this. These are the estimates you want to find. But there is a good trick, which is crucial for the proof, is that in fact it's very useful to consider half crossings. So, and of course, if you want to say that it survives, it must go out of the box. So you get an estimate. If you prove that these crossings have a small probability, you get the estimate you want. No? And there is one minor difficulty that you have, that you need to have an estimate on the crosses when you put these renewals below your box in time, and you need sort of uniform estimates because you don't have anymore the Markov property. You need to put these renewals starting somewhere below the box and make a uniform estimate. So these are just the same crosses, but in a uniform, taking the soup on all sort of renewals where you start. You do have some trivial comparisons, which I don't mind. The main problem here is the temporal crossings that you want to say. You want to get a recursion that it gives you the good estimates. So I want to have the half crossing of a time box of scale n in terms of scale n minus 1. And of course, you would like to have 2 of scale n minus 1 that gets a square, because as in the case of Marcelo today, if you have that, you are in good shape. No? So, and here is that if your Bn allows you half crossing to have at least 2 of those boxes before, you would be in good shape whenever you can isolate them. And you can always isolate them when you have renewals everywhere. So you get this estimate. That's for free. Okay, in space, it's easier. I mean, I didn't go into the details because these boxes here are not exactly boxes of scale n minus 1 because they are bigger in space, but using the half crossings and the geometric, you just have an entropic factor here, which are fixed and depending on the dimension. So, and then putting the two things together, you need to add the space and time, you get a recursion, and you need to make the selection of the b and the function f, so that this recursion is good, in the sense that if you have exponentially here, you do have the same exponentially decaying here. And the good choices that work for that are those functions that appear in the hypothesis. So that's from where the conditions appear. Once you do have that, you just have to find, given a small sequence to trigger in the language used by Marcelo to get the estimate. So you need lambda small. This is easy, and I am sorry because I think I went over time. I think that's all. I finish here. Thank you very much.
Thank you, Eulalia.